So this video will be part C of number 5 from the 2013 AB exam. So we have this region R again, and in part C it says the region R is the base of a solid. So really something is sitting on this, so it has a flat base and it's coming off of the screen toward us. For this solid, each cross-section perpendicular to the x-axis is a square. This phrase is pretty important. That perpendicular to the x-axis phrase basically tells us what we want to do is we want to cut down into this solid perpendicularly to the x-axis. So we basically want to take a vertical slice out of this solid. Now if you were physically able to have this solid sitting in front of you right now and you cut down into it perpendicularly to the x-axis and you removed the slice that was sitting here and you laid it out flat, what you'd end up seeing is you'd end up seeing a square face. So you have this square face, but this actually has a little bit of thickness to it because what we've done is we've removed it from the entire solid that's sitting on this base here. So if we were able to pick this up off the screen and turn it, this flat edge right here on the three-dimensional solid is really going to have to sit perfectly back down into the base of the solid and fill that slice. So the flat edge here on the three-dimensional cross-section corresponds to this in the two-dimensional coordinate plane. If we want to find the volume of the solid that's sitting here, which is going to be a goofy shape that I'm not even going to attempt to draw, we hopefully recognize that we're not going to have a formula from geometry for it, but if we can slice like we've done and we see what the slice looks like three-dimensionally and approximate the volume of this slice, we can integrate that approximation to add together an infinite number of these cross-sections volumes. And so what we're going to need to do to find the volume of this, the volume of our cross-section, that's going to be approximated by taking, if you want to call this the length times the height times the thickness, that'd be fine. These dimensions are going to both be the same. And since this shaded edge on the three-dimensional cross-section corresponds to this from within the coordinate plane, the shaded slice from within the 2D coordinate plane, I can find the height of this by saying what the height of this slice is. From top to bottom, that would be specified by a difference in y values. We want to take the bigger y value. The bigger y value is always at the top of our slice. The bottom y value is always going to be at the bottom of the slice, no matter where we draw the slice within the region. The bigger y value is on the cosine graph, so that's given by g of x. So the bigger y value is g of x minus the smaller y value. The smaller y value is this parabola, and that's given by f of x. So the height is g of x minus f of x. Since this is a square face, that's also the distance across the bottom. And then the tiny little bit of thickness that this has is going to be specified by delta x, since it corresponds to this dimension from the coordinate plane, and that's a tiny, tiny difference in x values, a tiny, tiny horizontal dimension that we're going to specify to be delta x. So the volume of this one cross-section of the solid is going to be the height that we got from out of the coordinate plane, so g of x minus f of x, times the length across the bottom, which is also g of x minus f of x, so it's really going to be that squared, and that would basically be the area of the square face here, and then times the thickness, which is delta x. This will get you the volume of any cross-section that you take from the solid at whatever value x is. We want to find the volume of the whole entire solid that's sitting on this base, and so what we're going to do is we're going to use the integral one more time, the definite integral one more time as a tool to add together an infinite number of these cross-sections volumes. So I'm just going to toss this expression into my integral. So I'm looking at g of x minus f of x, quantity squared. The delta x is going to become a dx, becoming the differential telling us what to integrate with respect to. The last thing we need here are limits of integration, and those would be the x values that all slices that we could have taken range between. Once again, smallest slice is going to have an x value of 0, biggest slice is going to have an x value of 2. And we do luck out again, just like we did in part B, because it asks us to write this integral but not evaluate it. We've written it out. This integral, if computed, will get you the volume of the solid that's described.